to do an example that's going to illustrate some points about vector notation that people often get wrong. And I'm going to go ahead and do it in the context of a full example of a vector calculation, but I want to emphasize the difference between a vector and the magnitude of a vector. So to be clear, everything that I've drawn on the board right now is writing down things about vectors. I have drawn vector A and vector B on this graph, and you can see this graph is labeled in meters, and to scale, I've set up my scale so that 5 centimeters here is 10 meters of actual distance, or maybe more simply, 1 centimeter on the graph is 2 meters of actual distance. So that's my scale. And you can look at the coordinates here of A and B. If I write these down in vector components, I'm writing this 2 component vectors instead of 3 dimensions, just to keep it simple. In vector components, vector A is 60 meters in the x direction and negative 32 in the y direction. And vector B is negative 36 in the x direction and 77 in the y direction. Those are my 2 vectors. And I'm going to go ahead, I'm going to want to talk about an equation like this one, C equals A plus B. That's what I want to talk about. But before I do that, I want to point out the difference between vectors and their magnitudes. So these are vectors in components. These are vectors drawn as distances as arrows on my graph. If I wanted to say what is the magnitude of vector A, there are 2 ways that I can do it. One way that I could do it would be to measure this on the graph. The magnitude of a vector, intuitively, is just its length. So as drawn here, this is hard to measure at an angle here, I'm seeing that this looks like it's about 33 centimeters on my graph. And my scale says that 33 centimeters, double it, would be about 66 meters of actual magnitude. So measured on the graph, I see that the magnitude of A is about 66 meters. That's scale on the graph. By the same token, if I want to do that for vector B, I could do the same thing. I can measure its length on the graph, and its length is about 42 centimeters. So that means its magnitude, 42 centimeters on the graph, is about 84 actual. So the magnitude of B is about 84 meters. That's just reading off the lengths of the vectors on my graph. And any graph of vectors, any picture of vectors is going to be like this. There will always be some scale. It may be that vector A isn't even meters. Maybe vector A is in newtons of force and B is in newtons of force or something. You would still have a scale in your graph that said that 1 centimeter on the graph was 20 newtons or something. I don't know. Whatever it was. In this case, I've got these magnitudes that are just the lengths of each of these vectors scaled by the scale of the graph. Now, I don't need to do that with a graph. Obviously, there should be better ways of doing this than just doing this with a graph. And indeed, I can use the vector components and the Pythagorean theorem to find the length precisely. If you look at this, if I make a right triangle, so the x component is here, and the y component, what is this? This is y of 60. Yeah, and the y component is here. Oh, goodness, I didn't draw that quite right, did I? Oops. Well, my magnitude is going to be off, isn't it? So this is supposed to be a right triangle, but is it really? A is 60. Yeah, I just drew this at a bad place, Oh well. So I'm expecting that magnitude to be off a little bit. So this is my right triangle, and I can use the Pythagorean theorem to find the length of A in 3 dimensions instead of a squared plus b squared would be a squared plus c squared plus d squared equals diagonal squared. In any case, here we go. My Pythagorean theorem says that the magnitude of A is going to be the square root of 60 meters squared plus negative 32 meters squared. And when I put that together, that's 3,600 plus 1,024. That's the square root of 4,624. I did this earlier. Meters squared. And the square root of meter squared is meters, so I have the right units. And when I take that square root, I get 68 meters. And my estimate was 66, and I didn't draw it right. So there we go. It's an extra centimeter longer to draw to be under the 60. So that actually sounds about right. Okay, got that. I can check the same thing for my magnitude of B. I can do the same thing over here. The magnitude of B by the Pythagorean theorem is negative 36 meters squared plus 77 meters squared. And if I do that, I get the square root of, I did this earlier in my calculator, 7225, 7,225 meters squared, which is 85 meters. So again, pretty close to what my estimate was. So okay, these are two ways of finding the magnitude of a vector. The vector itself is the arrow. It has a direction and a length. It can be written as an object in components, x and y components, or as x, y, and z if you've got 3 dimensions. Magnitude here is the length. Magnitude is the length. I measure just the length. That's the magnitude. I find the magnitude by doing the Pythagorean theorem. So that's the difference between these notations. A vector sign has components. It's an arrow. A magnitude is just a number. It's a length. Same thing for B. So if I were to add 2 vectors, the vector equations you have, like c equals a plus b, that's a vector equation that we can add up in multiple ways. One of them we've learned is that in vector language, you can take these 2 vectors and add them tip to tail to add vectors. So if I have c equals a plus b, what I can do, I can follow from the origin to the tip of vector A. I fixed it, right? My vector A was supposed to be here. Origin to the tip of vector A, and then I can add vector B to it. I can go tip to tail. I'm going to slide a copy of vector B over to here. That means it's going to go from here, and it's going to go to the left 36 meters and up 77 meters. And if I do that, if I put a copy of vector B tip to tail here, it's going to take me to this point right here. That's my copy of vector B. A plus B added tip to tail gets me here, and the result from the original tail to the final tip is vector C. This must be vector C along here. That's how I add vectors as arrows. That's how I add them graphically, just by putting the arrows tip to tail, and I get vector C. You can see vector C is going over here somewhere. I can figure out its components just by directly doing things here. My components of A, so what do I have here? C is equal to my components of vector A, in other words, 60 meters and minus 32 meters, plus my components of vector B, namely negative 36 meters and 77 meters. And if I put those together, all I do adding in components is I add the x components together. 60 plus negative 36 is 24 meters. And I add the y components together. Negative 32 plus 77 is 45 meters. There we go. That's my vector C, 24 and 45. And let's check. 24 is about here. 45 is here. That is what we got. So those are in agreement. Adding C equals A plus B as vectors, we add the components and we get this result. It's a vector result. What's the magnitude of vector C? Well, again, I can find my magnitude in multiple ways. One of them is just to measure it on my scale here. My magnitude of C looks like this is about 25 centimeters, it looks like. So my magnitude of vector C, 25 centimeters doubled for my scale, gives me about 50 meters measured from my graph. If I wanted to do it formally using the Pythagorean theorem, I can do that too. The magnitude of C using the Pythagorean theorem is the square root of 24 meters squared plus 45 meters squared. And that's going to equal, I did this earlier, 2601. That's the square root of that's not 2, of 2,601 square meters. And when I take that square root, I get 51 meters. So again, very close to what I measured in my scaled graph there. So this is the magnitude of C. Now let me ask, is it true? I'll put a big question mark here. Is it true that the magnitude of C is equal to the magnitude of A plus the magnitude of B. Compare these equations. These look very similar. The difference is here I have magnitudes. At the bottom I have magnitudes. Here I just have the vectors, not the magnitudes. Is this equation true? Well, if it were true, it would mean, I'll put a question mark here because we're asking, it would mean that 51 meters equals, question mark, A was 68 meters plus B was 85 meters. Is it true that 51 equals 68 plus 85? Obviously not. This equation is not true just because this one is. Vector equations require components. Vector equations require you to be adding the full arrows together. You can't just add the lengths and expect it to work, because these two arrows, A and B, are close to opposite one another. They're pretty close to opposite, so their sum, of course, is not going to, you're not going to be adding in the same direction. The idea is that vector equations are great because they have separate x and y components. That's what makes them useful. That's what makes them work. That's what makes them cool. The magnitudes are just lengths. And of course, we don't expect two lengths to add up to the total length unless by freak chance A and B point the exact same direction. That's the only time that this equation would be true. So this equation, as written here, is not true because that is not true. So never turn a vector equation into an equation with magnitudes. What we could do, we could say, it would be true to say that the magnitude of C was equal to the magnitude of A plus B. We could say that, but that's not as useful an equation to do. That's just saying, hey, the length of C is the same as the length of what you get when you add A and B. And that's just what C was. So this is true, but not very helpful. This is not true. You've got to use the vector equation in components to do vector calculations. And that's the difference between the magnitude notation with the absolute value bars around it and the vector notation. Is just one of them is the length of the thing, and one of them is the full length and direction, the full component form. That's what we've got, and I hope that's helpful in understanding how vectors work.